Okay, so this is part 2 of our nuclear physics video. Sorry, I just wanted to break it up into 2 videos just because we're getting really long. So let's talk about fission and fusion. So very, very large atoms, as we said, very large atoms will want to undergo fission. They want to fall apart. They want to reduce their binding energy. Sorry, they want to increase their binding energy. They want to go this way. And smaller ones want to increase their binding energy and go this direction. So something very large like uranium-235, what we can do is we can actually induce fission. We can make this even. Uranium-235 has a half-life of some billion years, some ridiculous amount. I forget actually. Uranium-238 is something like 5 billion years. Uranium-235 is still, it's a very, very large half-life. So what we need to do is we have to somehow make it fall apart. And we do that by making it an unstable isotope of uranium. And you do that by firing a neutron at it. You fire a neutron at uranium-235, that neutron gets absorbed into that nucleus. It becomes uranium-236. Uranium-236 can't stay together. It falls apart. And it typically breaks up into things in this sort of ratio, in the 140 and 92 ratio. Which one of the possibilities is krypton 92 and barium 144. And it's going to release a lot of that binding energy, right? Because it's smaller, these are much smaller. There's a lot less energy needed to hold all those nucleons together, and it's released, making off quite a lot of energy, about 200 mega electron volts of energy. That's something in the order of 10 to the negative 13 joules. But when you combine that in an Avogadro's number of atoms, we end up with a lot of energy. This is where nuclear power plants. This is how they work. You take uranium-235, you make it unstable, it falls apart, it gives off energy. You take that energy, you boil water, you put it in a generator, power. Okay. Now, the fascinating thing about this is the fact that it not only gives off these two things, it gives off a bunch of neutrons. And what that means is one of these neutrons, I start off, I usually use something like polonium or some neutron source to have it initiated. But once it's initiated, that neutron can go on and, that neutron can then go on and cause fission in other uranium-235 nuclei, right, in the fuel cell. And once you keep doing this, right, it'll keep going. It becomes a spontaneous reaction in itself. And it should, if you think about it, so 1 makes 3, makes 9, makes 27, makes 81, and so on and so forth. This becomes an exponential growth by a factor of 3. And if you can't get that under control, that's a runaway chain reaction. That's an atomic bomb. That's how an atomic bomb works. You take uranium-235 and you get a uncontrolled runaway chain reaction. Now that's not going to happen because it's very unlikely for those neutrons to hit another one, right? They're going to go off and they're going to pass through the material, and eventually they might hit one. So to make an atomic bomb, you have to compact the uranium using some sort of explosives, squish it down to a higher density so that there's more likely a neutron causing another fission. And you have to create what's called a critical mass. You squish it down to a certain density and we get a runaway chain reaction, you have an atomic bomb. However, in nuclear power plants, that doesn't happen because there's ways that you can control the neutrons. Use things, control rods. This is a neutron absorber that's put into the fuel rods, and that absorbs some of them. So there's this careful balance that nuclear reactors work on, is that they keep it going at a constant rate, so that one neutron goes to another neutron, and the other ones are absorbed or lost or something happens to them. So you want to keep that going. You want to keep this chain reaction happening over and over and over at some sort of constant rate. What happened in Chernobyl, which is a nuclear power plant in Russia, is somehow the control rods got stuck. they think. I don't know. You can go on YouTube and watch some of the how it happened. There's a brilliant TV show on I think it was HBO just recently. But I think what happened is the controls got stuck and they couldn't control the chain reaction. It got out of control on them and it exploded. Next, fusion. Sorry. So nuclear fusion is the opposite, right? This is when we combine these combined small nuclei, and that's going to give off energy because the binding energy is increased, right? So as we as we as we combine them, they're held together better per nucleon. The binding energy increases, so it's more viable to have a larger thing. This is again how the sun works, right? We want to, as we combine more and more nucleons together, we're increasing the stability basically, and the binding energy is going up. So there's more energy holding it together. So we're going to release energy as we combine these things together. That's how the sun works, right? We take hydrogens, combine them together. When they come together, they're going to be more stable, and they're going to give off that extra energy, right? So what we want to use in our one-day fusion reactors is when we take deuterium, which is a neutron added to hydrogen, so it's got a proton and a neutron. And then you take that and you combine it with tritium, which has 2 neutrons and a proton. And you combine them to make a helium nucleus and a neutron. And this gives off quite a lot of energy. And as you can see, you can do your own calculation here to look at the delta E on this one. But the delta E on this one is again going to be positive, and it's going to give off, I think it's something in the order of, I want to say 260 mega electron volts. No, I forget exactly. Look that up. Now again, we can use this in a what we call a hydrogen bomb. Okay, but again, the difficult thing about nuclear fusion is the thing that holds everything together. Keeps everything apart is the electrostatic force pushing the hydrogen atoms away from each other. So you have to squeeze them together. So a hydrogen bomb does this using a fission bomb, a uranium bomb. That creates a huge amount of heat. It creates basically a small sun, and that then initiates fusion in the tritium. The sun does this just by gravitational forces, right? The sun is powered by the gravity squeezing all these helium nucleus together, creates a huge amount of temperature and pressure. They're squeezed very, very close together. They're very, very energetic, and they are able to combine. And that happens, it's going to make helium always. Typically in our sun, our small sun, it happens via this process, which we call the proton-proton chain. You take 2 hydrogens, you bash them together, and that's going to make a deuterium nucleus here. That's a proton and a neutron. Sorry, proton and neutron. So 2 protons come together to make a proton and a neutron, which you may think is strange because yes, okay, so this is a neutron being formed. That means some sort of weak interaction happened. Again, that means that one of these protons transmuted into a neutron, giving off an electron and an antineutrino. Sorry, a neutrino here, right? Sorry, this is happening a proton into a neutron. So yeah, that would be a neutrino and a positron. Okay, so this is an anti-electron. Then that deuterium whacks into another hydrogen. That makes helium and gives off energy in the form of gamma ray. And this happens twice. We have these 2 helium 3s. That's helium with 1 less neutron. They combine, give off 2 hydrogens, and we end up with a helium. So overall, we start with 4 hydrogens, right? We start with 4 hydrogens, and we end up with 2. So we cancel out 2 of them, right? So really, overall, it's 2 hydrogens making a helium while giving off a bunch of energy in the form of gamma rays. Also giving off neutrinos. These are the solar neutrinos that we see in our neutrino observatories, and a positron that's eventually going to, very, very quickly, is going to hit an electron and disappear. Annihilate itself and give off even more energy. Okay? So overall, we have 2 hydrogens making a helium by this complicated chain of events. Larger suns, bigger than ours, undergo a slightly different version. That's a cyclical version based on carbon, nitrogen, and oxygen, which is fascinating. So you take nitrogen, you hit it with a hydrogen, that spits out a helium, basically by an alpha decay. Then that carbon that's formed here by this alpha decay, it's lost. Nitrogen's gained a proton, but then lost 2, so it's gone to carbon, and then again that hits. It's a hydrogen, gives off energy as a gamma ray. That makes nitrogen, carbon, nitrogen, oxygen, and it's this chain. So what do we have? We have input of a hydrogen, input of a hydrogen, input of a hydrogen, input of a hydrogen, and the output of a helium. Okay, so it's the same idea, right? We have 4 hydrogens coming together to make a helium. But we end up having sort of the same but different, right? And it gives off, again, a bunch of energy in the form of gamma rays, and we still have these neutrinos being formed and the positrons that are just going to cancel out. But overall, we end up with about 27 megaelectron volts happening there. Okay? So this is what provides all the energy on Earth, right? Mostly this one here. There is some the CNO cycle happening inside the sun, but mostly because our sun is smaller on the scale of suns, we have mostly proton-proton chain decays or fusion happening. And that energy that's given off here as these gamma rays, it bounces around the sun. Fascinating fact, the light that's given off by one of these things actually takes thousands of years to get itself out of the sun. It has to bounce around all over the place, and it lowers its energy, and eventually it's gone from these gamma rays down to the visible spectrum that we see, that provides the energy that we get on Earth, that provides life, right? Without the sun, there would be no life, there'd be no energy. It's the source of all energy in our solar system, right? And it happens all because the smallest, most simple nucleus in the universe, hydrogen, combines under these incredible pressures and temperatures to make helium. That helium can actually heliums can then combine to form higher and higher. That's where the atoms are made out of, right? This process inside the sun is where the elements in the universe actually come from, all the way up to iron. And after iron, they no longer fuse. Yeah, once it runs out of all the other things that it can fuse, and it's just left with iron stuck in the core of the sun, it stops functioning. The fusion engine, the fusion oven there stops working. The sun explodes, and we're left with that little cinder core left. Then you might think, okay, so where do the how come there's things heavier than iron in the universe? And they come from supernovas. When that explosion happens, that can then combine those even more energy, higher energy, and that can actually overcome this difference in binding energy, and it produces the larger atoms. We are, in the famous words of Carl Sagan, we are stardust, right? All of the atoms in us were forged in the solar oven. All the stuff that makes everything that you interact with every day only exists because of the nuclear fusion, that these hydrogen atoms, these protons, come together under incredible energies and make new nucleuses, new atoms, and all the way up to uranium and past. Okay, we are stardust. anyways, if we want to do this on Earth, right, these incredible pressures it's difficult to have this happen. The ways that we have two ways that we've tried to do this. One is with magnetic confinement. So you take hydrogen or tritium and deuterium, and you heat them up with incredible electrical potentials. You know, heat them up to thousands and millions of degrees until they become a plasma, which means that basically we've removed all the electrons. It's so high energy that there's no bound electron states anymore. So it's just a polarized, an ionized gas. And because it's charged, or protons and electrons floating around in there, you can then use magnetic fields to squeeze it down, to basically create a magnetic bottle that holds that plasma in there, and you squeeze it and squeeze it and squeeze it with those magnetic fields, and you heat it up and heat it up and heat it up, and you basically create a small sun on Earth. This is a tokamak reactor, where you create this magnetic donut, this torus, and you squeeze it down, you heat it up, and you try to recreate the conditions of the sun. But as you can see, that's an incredible amount of energy is input into it, and we aren't quite ready for. We haven't quite got to the point where the amount of energy that we put in is less than the energy we get out. Okay, and another way that they've tried to do this is with lasers. Is they try to fire incredibly powerful lasers at basically some hydrogen, some deuterium and tritium. Whoa. Uh-oh. My mouse just went crazy on me. Well, sorry about that. So you try to combine the hydrogens via these lasers. Okay, 1 second. So this is the Lawrence Livermore. What's it called? The Lawrence Livermore Inertial Confinement Fusion Project. They've stopped as of 2012 using this for this project, so not sure what the future is of this laser fusion. But the magnetic bottle idea is being built right now in what's called ITER, which is the International Thermonuclear Energy Reactor, experimental reactor, which is possibly one of the largest, most expensive physics experiments ever created. So you can see there's a person. This is the tokamak reactor, and they're basically creating superconducting magnets, toroidal and polar magnets, in this massive thing here. These coils have to be cooled down to, they're superconducting magnets, so they're cooled down to liquid helium temperatures, down to -4 degrees Kelvin. It's a huge project, and currently they actually have built already the bottom part. They're starting to build these pieces. They're not put together yet, but they're being built as we speak. And they think that by 2025, they'll have the first run going for this massive project that's been in the works for, cost something like $65 billion, and it's been in the works for the last 30 years or something like that. But hopefully, we'll see soon some actual results of this massive project in producing basically a small sun here inside the Earth. All right. So that's all I want to talk about for nuclear physics. I apologize for the incredibly long lecture, but there's a lot to talk about. I could spend an entire course talking about this stuff if I wanted to, but really this is the last thing I want to say to you in grade 12 physics. So hope this course has been fun. I hope that you've learned something, and hopefully we'll talk sometime. All right. So best of luck. You guys are all in maybe grade 12, so best of luck in wherever you guys are going to go. And this is Mr. Stone signing off. Last time.